Okay, so we're going to continue with this. So the previous lecture left off with this idea that we can use configuration spaces to understand embedding spaces, and as I mentioned, other people have used these ideas for diffeomorphisms and that kind of thing. And eventually I'll do some things with knots. So let me do this. So, but first, one last little thing about homotopy fibers, homotopy limits, and all that jazz. So here's something that we need. So let's recall then the total fiber of a cube. So this will be, for those who didn't make it, the first one. The next 5 minutes might be harder to follow, but I think it'll get better after that. So the total fiber of, just say, a square of spaces is, well, it's really inside the space of maps from literal square into x12, and then an interval into x1, or an interval into x2, and then just a point in the first space. And it's the space of all such, so that, for example, if I take x here and I call these, I don't know, let me just call this F and G to the left. And I don't know, H and L if need be. That x here means that these maps, call them gamma 1 and gamma 2. Gamma 1 starts at f of x, and gamma 2 starts at g of x. So this, I wrote it in the other direction, but really you should read this from right to left now. Our friends who are watching this who are fluent in Arabic will be comfortable with this, that you start with a point in x, and that gives you two places to start at x1 and x2, and then that gives you two paths, and then those paths map to x12 under h and L, and then the map from the square in x12 has to fill in from those two paths, has to extend to a map to the square. And I'm not going to write everything down because that's, I think, clear enough and folks can fill in. So for, but then here's another way to, another model, which will be useful. Namely, well, first define I'm going to just be very limited in my definition of holim, not general at all. Let me put that down here too, just for space. Let's consider everybody but the initial space. The holim of that is going to be similarly, I'm going to look at maps from an interval into x12 and 2 points, which again I can think of as maps from a 0 square into x1 and a 0 square into x2. And inside there, I'm going to look at the space of paths, which on those two endpoints have that path is from well, let me maybe say it. So if I've got a y cross z, and then I've got a gamma, so that gamma is a path from f of y to g of z. I may have reversed my roles of f and g, but things are symmetric. So that's the homotopy limit of this little diagram. It's also called the homotopy pullback. Because what is the pullback? The pullback would be the things in the product x1 cross x2 that map to the same place. As I said before, this is a funny thing where we say, well, it's maybe a bit much to expect us to map to the same place. So good enough for government work, I'm going to take wherever x and y map to, and then I'll just supply this gamma, which accounts for the quote unquote error by providing a path between f of x and g of y. So homotopy theory is very forgiving. Our pullbacks that we like the best, you don't require things to go to the same place. They can go anywhere as long as there's a path between them, and we'll provide that data of the path between them. So then I claim that, well, first of all, x phi maps to this homotopy limit. By, well, I'm going to go, if my x here is going to go to the constant path at wherever I map to in, so the image of x in x1, 2. So that's an element of the homotopy limit. It's in fact a subspace homeomorphic to x phi. And then the claim is that, this is, I think, basically a homeomorphism, that the total fiber of the cube, of the square in this case, is just the homotopy fiber of this map from x phi to the homotopy limit. And this is pretty straightforward at this point, just some adjunctions and playing around with homeomorphisms of the square and things like that. But the reason that we give this point of view, so we can view this homotopy limit, I won't write it one more time, as an approximation to x phi. Great. And let me say how this works in general, not just for squares. So I'm going to look at the non-empty subsets of the set from 1 to n. And I'm going to think about, I'm going to define the homotopy limit of some, these are what I might call subcubical diagrams. And it's going to be a subspace of the space of maps, of the product of faces inside delta n, and I'll give you an example of the space of maps from that face to xs, and it's going to be compatible. So the point is that that the nerve, so the key, so what is fs? The key is that the nerve of this 2 in and to the n, which are non-empty, is homeomorphic to a barycentric subdivision of an n-simplex, or an n-1 simplex, sorry. And in fact, I should put n-1 here. And I'll just show you the one picture, and this will be clear enough. So if I've got the non-trivial subsets of 1, 2, 3, namely I can have 1 or 2 or 3, or 1, 2, or 2, 3, or 1, 3. And I draw in all the inclusions and the composites of inclusions, which themselves are inclusions, and I fill things in. I get a lovely simplex, subdivided. And so, you know, for example, this thing here is what I was calling F13. It's that face of the simplex, the barycenter labeled by that subset 1, 3. So you can then take the space of all maps from, well, in the case of a 3 subcubical diagram, so a 3 cube, if I remove the initial vertex, what's left looks like a 2 simplex. I can take 2 simplices mapping to the final face, x1, 2, 3, the final space, and then 1 simplices mapping to x1, 3, x1, 2, and x2, 3. 0 simplices or points mapping to x1, x2, x3, and demand that all sorts of things are compatible. So again, the way I would start is take a point in x1, a point in x2, and a point in x3. Next, look at the image of the point in x1 and x2 in the space x1, 2. Those, if I'm going to have anything, need to be in the same path component. Choose a path between them. Do the same on the other 2 faces. Finally, that's the image of those 3 paths will be a triangle in x1, 2, 3, assuming that can be filled in, fill it in to get an element of this homotopy limit. Phew. So why do I say this? Well, this model for the total fiber then tells me, again, that I can think about so let's recall from last time, which wasn't that long ago temporally. And of course, folks who are watching lectures, if you can be binge watching now and you know, you don't have to end on cliffhangers all the time, you can see what math comes next. So last time, the main thing I sketched was that we had this E empty, which was the embedding space. And it could restrict all sorts of places, and they could restrict to each other by cutting out subintervals. So here is generally ES, which was embeddings of an interval, but then I punch out J sub I for I in S. I'm going to punch out the union, sorry. And I'm going to embed that. And once again, the main point was that this was a configuration space of some number of points in the box, which is the same as Euclidean space. And then I also have the tangent vectors at those spots. So I had a large cubical diagram potentially. And what we showed is that this was highly Cartesian. So we showed that the total fiber increases in connectivity when I'm in dimension greater than 3. Now, again, for any geometric topologists, this doesn't apply to knot theory, although we'll get to some knot theory before too long. But again, these spaces are starting to have some impacts in 4-dimensional topology by work of Boudny and Gabay. But then the point is that what this means, by what I just said, is that E empty, again, which is the embedding space that I care about, this space of knots, to the homotopy limit of the rest is highly connected, a highly connected map. In other words, we can use the homotopy limit of the rest as an approximation, as a model for the embedding space. And the first thing I want to say is that there is some then geometry to this that shouldn't be apparent to you at this point. So let me make this even smaller because I want to try to fill in a diagram here. So I'm going to write this in a funny way. So EMBIID, I'm going to let again n equal 3. So I've got embeddings of an interval minus, say, J1. And then, and really this maps to, not just to one space, it maps to all spaces compatibly. It restricts everywhere. Pardon me while I fill this in, but it's hard to, I don't want to just say this diagram, that diagram. Show you the diagrams. Every map in here is a restriction map because I'm sort of cutting away more and more. And then finally, I cut away as much as possible all of the J's. And I get a diagram like that. Phew. And these are all restriction maps. Well, let's remember, I showed you last time, I indicated anyways, that this top space was really like configurations of 0 points with a tangent vector in the cube. Let me make this even smaller. I kind of like this whiteboard business. I know this is going to be hard for you to see, but it's actually the right scale to compare. And then if I punched out 2 holes, I had the point that's in between them, and that was configuration of 1 point with a tangent vector in ID. Again, these are really just contractible. A single point, singleton points, not even contractible, but highly contractible. And then finally, I have 2 points with tangent vectors at each one. And so the spaces in this diagram are homotopy equivalent to the spaces to the left. Again, the idea being, I know there's at least one person here who would appreciate this. If I have an embedding, I'll write it here, that is, if I've got a few intervals punched out, then this space is homotopy equivalent to, well, I'm just going to remember where those endpoints of the intervals map and the tangent vectors. And then I've got for example, in this case, a configuration of 4 points with tangent vectors at those 4 points. So, so these diagrams look the same, but there's an important distinction here. What would the maps be if I were looking at the diagram to the left and trying to make a diagram to the right? So let me let's redraw this little square here. Maybe I'll have only one of them. And so I'm thinking about this midpoint or some point and a tangent vector there. So that's great. And now I'm punching things out. So that's just a restriction map. So my interval splits in two, and the idea would be that this tangent vector splits in two. And so you're repeating things. And so what you want to say here is that this map should be, I'll only put in question marks, well, should be repeat, or that's just another name for the diagonal map. But then you realize that in configuration spaces, you have removed the diagonal map. What does it mean to repeat a point in configuration? Well, it doesn't mean anything, but the remarkable thing about these Fulton-McPherson compactifications is, so I'm going to replace all of these parentheses by angle bracket parentheses, that there are diagonal maps. Remember from a few lectures ago that we could fill in the, we could add some points at infinity. You're allowing points to repeat, but then you need a vector between them if they collide. But I've got configurations with a vectors decorating, so I can use that vector as the infinitesimal configuration. So the picture of this becomes, if I start with a point and a tangent vector, I produce under the diagonal map a configuration with 2 points at, quote unquote, at that point, and their relative tangent vector is the same as the original tangent vector, and at each point I've also got that same tangent vector. So this is a funny thing we can do with these compactified configuration spaces. We have diagonals, and those diagonals are what come up, at least up to homotopy in the left-hand diagram. Now I've got a well-defined right-hand diagram. I also have a map from the embedding space to this diagram, namely take F to the configuration space functor of F. And let me be clear that I want to do this with the compactification. So in other words, I have my knot. Let me write this above. I'll again just kind of draw this in 2 dimensions. I have my knot. All right, maybe I'll draw it in 3 dimensions. And I want to produce a map, for example, from configurations of 2 points in the interval compactified to configurations of 2 points in the cube compactified, which I can because I can just evaluate f at those 2 points. So you give me 2 points on an interval. Let's draw them here, green and yellow. Well, I'll give you 2 points in space, green and yellow. And, but this compactified configuration space, the version that is best here is one, as I've used angle brackets, where this becomes delta 2, right? The space of all pairs of times on an interval is delta 2. So given a knot, I can make a map from delta n into the infold configuration space, namely take the times t1, t2, etc., and evaluate the knot at those times. That's going to be a configuration of distinct points, honestly distinct as long as the times are distinct. If any ti equals ti plus 1, then I'm not in the standard configuration space, but I'm in a subspace of the ambient configuration space where those points, quote unquote, agree. So the point is that in this diagram, all of these are really inclusions. In other words, there are subspaces with these compactifications. There are subspaces of configurations of endpoints, which are homeomorphic to configurations of n-1 points or any lower number of points. And in this evaluation map or induced map on configuration spaces, the various faces of delta n have to go to those various faces. So then the theorem, and this is something that I proved, is that, let me maybe make this bigger now. Let's see, let me get a position. So the theorem is that the maps from the embedding space to the left homotopy limit and embedding space to the right homotopy limit, not left and right as in functors, but just I've got a subcubical diagram on the left, namely these punctured embedding spaces, or on the right, these are the configurations, that these agree in the homotopy category. In other words, the targets are homotopy equivalent, and those maps are homotopic to each other via some homotopy equivalence. So, so in other words, this punctured knot game is giving us this induced map on configurations game. And again, the first example of induced maps on configurations is a classical way to evaluate a link at 2 points on the 2 links, and you get a map from S1 cross S1 to configurations of 2 points in R3. So, so yeah, so remarkably, these fun and games with cubical diagrams gives a way to now really not only approximate the homotopy type of the embedding space through some things which have configuration spaces as their components, but the map from the embedding space to that homotopy limit is really just evaluation of the embedding of the knot. So let me tell you one of the question that I guess if I could ask a genie to solve anything for me, and wasn't allowed to say something canned like the Riemann hypothesis. So here's a question, and we're making progress on this. So so in other words, let me then say, so for d bigger than 3, this these induced maps on configuration spaces capture all of the algebraic topology capture the full homotopy types of these embedding spaces. Let me put the question out now, but I want to come back to it later. But this is the main question. Again, if I had one question that I could ask a genie to answer for me, and I wasn't allowed to say Riemann hypothesis. So question, if I've got this, the classical knot space, so this is a knots in a box, but the set of components is the same as the classical sets of knots. And now I can look at this HOLEM, which is really just the space of maps from delta n into configurations of endpoints in a cube, such that dot dot dot. And again, I'm taking a map F, and I'm evaluating it at endpoints. I've also called this just the induced map on the configurations of F. The question is, how does this, what does this C on pi 0? Maybe I should ask my genie a better question, but that's the basic question. In other words, suppose I could elaborate the components on the right. Then this gives us some set of knot invariants. Which sets of knot invariants are they? Well, let me skip ahead and I'll come back to this. They are as powerful as all of the quote unquote classical quantum knot invariants, so the Jones polynomial and its generalizations coming from other Lie algebras. You know, and it's through the Bott-Taubes and Kontsevich integrals, which again I'll discuss later. But it does seem like we're getting some parts of the story over the integers. All of those integrals really rely on constructions over the real numbers, and this homotopy theoretic construction of this mapping space and its algebraic topology is something that's starting to let us see more of the picture over the integers. Although again, there are important things that I want to say for higher D before we get to this. Okay, let me move on the board. In fact, let me go ahead and go, because I've taken so long. We'll see how this works out. I'm going to go to the second board. Okay, so what this says is automatically so there's a spectral sequence involving starting with, well, it looks pretty big, the direct sum over I of the direct sum of over n choose I copies of configurations of I points in the cube. And I'm going to look at homotopy. And that's going to converge to the homotopy of the space of embeddings of an interval in ID through a range which increases with n. Well, let me say that over here. So there ends up being two types of reduction of this. And I've decided that I didn't have time to talk about this. This is more very combinatorial, categorical, algebraic topology. And the reduction is actually ultimately, and let me go say where it comes from just for reference. There's a cosimplicial reduction. Turns out that these cubical diagrams happen to be of a very special form that they're pulled back from a cosimplicial diagram. So just would take us a little bit too long to define all of that. But let me just sketch what you get is a spectral sequence that goes from the homotopy of configurations of one point with tangent vectors and ID. And I don't need to take a big direct sum, just the homotopy of configurations of 2 points, the homotopy of configurations of 3 points, etc. I take all of these, and I also have to take some fibers between them. And what this does, well, actually, let me not even fully reduce. Let's just start there. So I take those homotopy groups, I put them at the -1, -2, -3 columns. These diagonal maps give me a chain complex structure, and the homology of the chain complex is the that chain complex is the E1, and then the homology is the E2. And it turns out that so again, let's remember that D is bigger than or equal to 4 if I want to know convergence. It happens that after I do that, I've got zeros above and below some sector that actually increases. This is slope that's steeper than -1 or whatever. So it's less than -1. And so that actually guarantees finiteness in each degree. So it guarantees convergence, which isn't a subtlety here. So homotopy limits, their homotopy groups are made to fit together in exact sequences and that kind of thing. More subtle, alternately, well, we already talked about this. Let's recall. That if I take the free abelian group on a space, my favorite model for Eilenberg and Klein spaces are the free abelian groups on spheres, and the homotopy of that is isomorphic to the homology of the original space. So one thing one can do, so we have this embedding space. This is the Dold-Thom theorem, by the way, basically, plus a bit of a group completion. We have that the embedding space maps to this homotopy limit of configuration spaces. right? And this is a good approximation. So this is if I cut this off at n, this is good through a range. Well, under connectivity hypotheses, if I want to compute the homology of the embedding space, I can play this game. Well, it's automatic that this will be comparing the same range to the homotopy Z, the free abelian group on the homotopy limit. But then the remarkable thing, and this sort of goes more generally to sort of generalized Eilenberg more spectral sequences, is that that compares to the homotopy limit of the abelianization of each of them before taking homotopy limit. This, alas, homotopy limits are mapping spaces, so that's limits. The free abelian group is a union, it's a co-limit. And one thing that we all tell our children as they're growing up, don't touch the stove and don't commute limits and co-limits. But this actually does work with some connectivity hypotheses which hold here. So this is a generalized Eilenberg-Moore spectral sequence, and this is valid again for these high dimensional embedding spaces. And so then the fun thing is that you get a spectral sequence that involves the homology of configurations of endpoints with tangent vectors in ID. That's what's in these columns. Again, the D1 maps are going to go this way. They're the diagonal maps. And let me just tell you a little bit about how that looks geometrically. Well, so let's let D equal 4. And let me tell you about what is on the E2 term. So let D equals 4. And then let me just say what survives to E2, or at least some of what survives. And the first thing that survives is a class. So let's remember that the homology of the configuration space, this was this Poisson-Operad given by Forrests. And the first thing that survives is a Forrest or bracket expression. Here it's in degree -4, and this will be let's see, if it's R4, this will be degree 6. So this would be, and this is a bracket expression, x1, x3, x2, x4. So there we have it. And that ends up being a z that survives to E infinity. So that implies there's some class in H lower 2 of the space of embeddings of an interval in I4. And well, again, this is a geometrical topological question. What is the homology of the space of embeddings in a sense? So to know that there's a class there is one thing. Can we see it in a sense? And the answer is yes. This is a construction due to Cattaneo and his collaborators. I think Bott might have helped express it. So notice these brackets, x1, 3, one with 3 and 2 with 4. What I'm going to do is I'm going to take my knot in R4, which again, I'll just sort of draw in R3 or something like that, but this is really I4. What I'm going to do is I'm going to first look at a singular knot. So it's not in the space of embeddings. So 1. Okay. So you notice here that if the knot is proceeding down, as I go here, this double point happens, there's T1, T2, T3, T4. So 1 and 3 are paired through the singularity, and 2 and 4 are paired. So I want to make an element of H2. That means I want a two-dimensional family of embeddings. That two-dimensional family of embeddings is going to live in a sort of a small neighborhood of this singular knot. And so for each of these double points, well, they span some two-dimensional subspace of R4 locally. That means I've got a normal 2 dimensions. And if I look in those normal directions, I can take one of them and bump it off in that direction. And if I want, I can bump off the other strand in the opposite direction. Actually, why don't I just draw the 1? So for every normal vector, say a unit vector, I have a way that I could have avoided this collision. And so that means that I've got a map from S1 cross S1 to this space of embeddings of an interval in I4 that realizes, I claim, this through you know, say VW goes to the resolution, resolve the first double point in the V direction and the second double point in the W direction. And I claim that the fundamental class of this gives me a class in the two-dimensional homology of the space of embeddings, and that's a generator. So that generates that Z in the spectral sequence. And it's still open, actually. I had one student work on a thesis that did similar interpretation higher in the spectral sequence. But to this day, and I'll say something more about the spectral sequence in a second, we don't have explicit homology and cohomology representatives. There's conjectures, there's some precise conjectures for rational cohomology and some vague conjectures for rational homology, but nothing over the integers even for conjectures, precise conjectures. Okay, let me now start to give closer to than what our full knowledge is. And it'll just be a so these homology spectral sequences are now known to collapse over Q by formality results. I just wanted to say a little bit about those. I think I won't say nearly as much as I want because I do need to end on the hour today. So first, rationally, I've mentioned this before, rational homotopy. You've got your spaces are now modeled by, for example, commutative, differential graded commutative algebras, so chain complexes with multiplication, and then diagrams of spaces are modeled by diagrams of those, which you can really think of as generalizations of bicomplexes. And when, if I've got a bicomplex and I look at the spectral sequence for the bicomplex, if the constituent complexes are formal, then the spectral sequence will collapse. So let me indicate this remarkable fact. So both the configurations of endpoints in RD and these diagonal maps which occur, in fact, all operad structure are formal in the rational world. And we haven't talked a lot about rational formality, but let me say that let me at least indicate the following. So here's a definition which isn't standard. Strong formality is when you can map your homology of X into your cochains of X. And I'm thinking about something like, say, de Rham cochains, which are commutative. And this is an equivalence, and that includes of the multiplicative structure. So that's unusual. So this implies formality, and in particular, it implies, for example, that there are no Massey products, because Massey products are defined by co-bounding things, and there are no co-boundaries in the cohomology. The cohomology, by definition, is a complex where the differential is identically zero. Well, it turns out, let's consider configurations of endpoints in the complex plane. We've thought about this as R2 before. It turns out that this, for example, is strongly formal. And that's because I can, if I've got the cohomology, remember it's Z adjoin, you typically say Aij. Aij is in H upper 1, modulo this Arnold identity. Again, folks who are watching YouTube can go back to where we talk about the cohomology configuration spaces. It's also with graphs, Ij, and then when you take a product, I can, this is the same as Aij, Ajk, Ajl. So that's another way to discuss the cohomology. So in this case, I can map it to the cochains, the de Rham cochains, but I'm going to use complex valued functions of configurations of endpoints in the complex numbers. And what we're going to do is we're just going to send Aij to the form, you can write it a couple of ways, d log of, so again, the configuration space is equal to Z1 through Zn, which are distinct. So if I take Zj minus Zi, that's some other complex number that's non-zero, and I can take the differential of the log. Now the log itself is a multi-valued function, but its differential ends up being then perfectly well defined, and it's just really dzj minus dzi over zj minus zi. And now the Arnold identity holds on the nose at the cochain level with this choice. And that's very special and in 2 dimensions. You can just, yeah, again, the Arnold identity is just that aij, ajk plus ajk, aki plus aki, aij is equal to 0. And that's special. So in general, and so that actually then gives strong formality in this case. So in general, Kontsevich noticed and then told Bot Taubes, and they worked out part of this, and other folks noticed that that aij, ajk plus ajk, aki plus aki, aij is just d of something. I'll call it theta 1, theta I, j, k. And the fun thing is, instead of all of these indices everywhere, what one can do is, as I said, we have a, I, j, a, j, k would be represented by a graph where I is connected to j and that's connected to k. And then I've got the cyclic permutations. And now this is at the cochain level. Well, that ends up being, in a sense, d of something where I'm going to take I, j, k. I'm going to have some external vertex that I'm not going to bother to label. And let's see. I should maybe, I'm going to change the arrows because I want to be able to contract. And so in this case, really what I want, and this is equivalent, is each of these vertices in when it's involved in both terms of the product, the edges are oriented away. And the point is that there's a graphical, this is something that you can define combinatorially, where we, the D is defined by the sum over contraction of edges. So in the case of configurations in the plane, there's this, and the plane happens to be the complex numbers, there's this remarkable fact that you don't need any co-bounding for the Arnold identity. In higher dimensions, you must co-bound it. But Kontsevich was the first one to notice that you could co-bound that. Well, that's easy enough. And then consistently co-bound all the other relations that occur in the cochains of configuration spaces. He does this through differential forms that first arise in quantum field theory. So you go from graphs to forms using differential integrals, using integrals that first arise arising in literally quantum field theory, sort of Feynman diagram kind of integrals. So it's a remarkable story. I noticed that that we have Florian here to, he can maybe one day tell us about that story further. He's an expert in this. But the remarkable thing is that that story then comes in this circle of ideas, allowing us to understand spaces of embeddings in higher dimensions. And I'll say a little bit about how that works for knot theory in a bit. Yeah, I think that's all I then want to say for now. I know this is sort of it wasn't as many details as we perhaps like, but I'll stop it there. I'll be very brief for questions because I do need to move on. Perhaps I'll stop the